Hi and Assalamualaikum. I'm Nur Fikriya Akmasar binti Alidan 20231656111. So today I'm going to present about fundamental of radiation physics in the cancer radiation therapy. But the first thing first, we need to know what is the meaning of the radiation therapy for cancer. Radiation therapy for cancer is a treatment that uses high energy rays like X-ray or photon beam to kill cancer cells or stop them from growing. It targets the cancer area to damage the cell DNA so they can multiply while trying to protect healthy cells around it. So my part is to explain about the fundamental of radiation physics in a cancer radiation therapy. Radiation therapy, along with a surgical therapy and chemotherapy, is a major component of the modern day cancer therapy for a majority of cancer patients, approximately 50%. Therefore, it is essential to understand the role that radiation physics plays in providing the patient with the appropriate amount of ionizing radiation to the tumor while minimizing exposure to healthy tissue. It is critical to understand the difference between the various types of radiation available and how they interact with human tissue in order to provide a safe and effective treatment. Next, type of radiation used in therapy. Several forms of ionizing radiation are used clinically, each selected based on the tumor's type, size, location, and biological characteristic. The first type radiation therapy used is X-ray, which is photon, produced by medical linear accelerators, which is LINAC. X-ray generate a high energy available in a range of 6 to 25 MV are the form of radiation most used for delivering external beam radiation therapy, which is EBRT, to patients. Because of their great penetration depth, they are beneficial for treating deep-seated cancer, such as a prostate, lung, or brain cancer. X-ray deliver a cumulative dose as they penetrate into the body. Second is gamma rays. Gamma rays are produced by spontaneous radioactive decay from a graphene isotope such as cobalt-60. Many hospitals still employ gamma rays for limited specialized therapeutics use, such as the gamma knife radiosurgery, which target a small area of the cranium and can be delivered with a precise sub-millimeter diameter. Next is electron. Electron beams, which are lighter than the mass of X-ray and gamma rays photon and carry significant charge, have limited deep penetration capabilities within the body due to the amount of the energy deposit of 1 to 5 cm based on the electron beam's energy. Because of this finite penetration in tissues, electron beams are generally used to treat cancer of shallow depths, such as skin and lymph nodes close to the skin, without damaging tissues and deeper level, provided the electron beam is the proper energy for the treatment. Last but not least, the type of radiation used is proton. Proton are positively charged particles that possess mass and are characterized by a distinct method of delivering energy, which is dose deposition, known as the break peak. Initially, protons deposit a minimal amount of energy when they enter the body. Then they deposit a large proportion of energy at designed and adjustable depth, with nearly all subsequent energy being deposited below this depth. Because of these exceptional precisions, proton therapy is particularly useful for treating children with cancer tumor that are adjacent to vital organs such as the eye and the spinal cord, and tumor that require minimization of adverse effects due to the long-term exposure. Next, I will explain about interaction of radiation with matter in the human body. Firstly, the photon is absorbed by an electron in the inner shell, which is the absorption occur, and then is it eject from its parent atom. The photoelectric effect is a very important at low energy, and due to the type of energy being used, it does not have any significance in megavoltage therapy, but it has an important role in imaging studies and in areas that have high atomic number, for example bones, as it adds to the contrast in diagnostic X-ray imaging. Next is Compton scatter. Compton scatter is a major interaction for megavoltage therapy in the 1 to 25 MeV range. In Compton scatter, a photon strike an optically free essentially free electron, which allow it to lose some of its momentum as described above and to redirect scatter to the new direction. In this displacement, the Compton electron continues to ionize the surrounding area. The uniformity of dose distribution provided by Compton scatter and hence the relationship between dose distribution and the electron density of tissue allows for effective treatment of the vast majority of solid tumor. The third process is a pair production. Pair production which occurs when the energy of a photon exceeds 1.022 MeV. When a photon comes into contact with a nucleus, it will produce an electron or positron pair via the process of pair production. Subsequently, the positron combines with an electron and it annihilates, emitting two photons. Pair production is becoming more significant at energy above 10 MeV and is a mechanism by which radiation dose is deposited into the tissue of the body. Even though Compton scattering is still a much more dominant mechanism of interacting with radiation in clinical X-ray beams. As you can see, this is the clinical relevance. In summary, the successful application of radiation therapy hinges on a deep understanding of radiation physics, linking the fundamental behavior of radiation in a matter to biological outcome in the cancer treatment. As technology advances, this knowledge continues to drive innovation that improve precision, efficiency, and patient quality of life. That's all from me. Thank you.
Hi, my name is Nur Zahida binti Saleh. This presentation will be focusing on medical linear accelerator or LINAC as an application in nuclear technology. By definition, a LINAC is a device that utilizes electromagnetic waves to accelerate electrons to near light speed. In a clinical setting, this high-precision technology is used to treat malignant tumors by delivering high-energy radiation that destroys the DNA of cancer cells. To understand the operation of this machine, the process can be divided into three distinct stages. Firstly, the physics of compact acceleration inside the waveguide. Secondly, the conversion process at the tungsten target. And finally, the precision beam shaping of the multi-leaf collimator. First off, let's take a look at the inside of the waveguide. Here, microwave power oscillates at 3000 MHz to create a standing wave, which is a stationary electromagnetic pattern within alternating resonant cavities. Electrons are injected in time bunches, entering the accelerating cavities at the precise moment the electric field reaches its maximum forward pushing strength. By reflecting energy to double the field intensity, the system allows electrons to gain massive megavoltage energies. This efficiency is the reason a powerful particle accelerator can be contained within a tube only 1 meter long. Once the electrons exit the waveguide at nearly the speed of light, the process enters the conversion phase to generate the X-ray photons required for treatment. The electron beam strikes a tungsten target. This interaction relies on the principle of Bremsstrahlung radiation. As seen in the diagram, when the negatively charged electrons approach the positively charged nucleus of tungsten atom, the resulting attraction causes them to deflect and slow down. This sudden loss of kinetic energy is released as a high-energy X-ray photon capable of deep tissue penetration. The final stage, these raw X-rays are shaped for patient delivery. This task is performed by the multi-leaf collimator, or also known as MLC. The MLC consists of two rows of individual tungsten leaves that move independently to block portions of the radiation beam. By precisely sculpting the beam's edge, the MLC ensures the high-dose radiation conforms strictly to the tumor's unique geometry while shielding the surrounding healthy tissue from harm. In summary, the medical LINAC represents a seamless energy transformation from microwave power to high-speed electrons and finally to a precision-shaped X-ray beam. Through these three stages, lethal doses are delivered to cancer cells with sub-millimeter accuracy. So this concludes my overview on medical LINAC. Moving on, our next presenter will discuss about dosimetry in radiation therapy.
Assalamualaikum, I greet to Dr. Zulaika and my dear fellows. My name is Nurhani Shazwani binti Muhammad Nasli. My student ID is 2023368351. Next, I will present about dosimetry in radiation therapy. Dosimetry in radiation therapy is the science of measuring, calculating, and verifying the amount of radiation dose delivered to a patient during cancer treatment. It is a critical part of radiotherapy because accurate dose delivery ensures that the tumor receives a sufficient dose to destroy cancer cells while minimizing radiation exposure to surrounding healthy tissues. Proper dosimetry also helps maintain treatment safety and consistency throughout the therapy process. After that, measurement of absorbed dose. The absorbed dose refers to the amount of radiation energy deposited per unit mass of tissue. It indicates how much energy from the radiation beam is actually absorbed by the patient's body. Accurate measurement of absorbed dose is essential to achieve effective tumor control and to prevent complications caused by overexposure or underexposure to radiation. In clinical practice, absorbed dose measurements are carried out during machine calibration, treatment planning, and routine quality assurance to ensure that the prescribed dose is delivered correctly. Next, in radiation therapy, the absorbed dose is measured using the unit called the gray, abbreviated as GY. 1 GY is defined as 1 joule of radiation energy absorbed per kilogram of tissue. The gray is the most commonly used unit in radiotherapy and is used to prescribe and monitor patient treatment doses. Another unit, the sievert, is used to measure equivalent and effective dose by considering the biological effect of different types of radiation on tissues. However, the sievert is mainly applied in radiation protection and safety rather than in routine cancer treatment. Therefore, in radiation therapy, the gray is the most important dosimetry unit. Furthermore, comparison between ionization chamber and thermoluminescent dosimeters (TLD). Ionization chambers and TLD are both used to measure radiation dose in radiotherapy, but they have different roles. An ionization chamber works by measuring the ionization of air caused by radiation, and the collector electric charge is directly proportional to the absorbed dose. It provides highly accurate and real-time measurements, which is why it is mainly used for machine calibration and quality assurance of linear accelerators. However, due to its relatively large size, it is not suitable for use on patients. On the other hand, a thermoluminescent dosimeter or TLD measures radiation dose by storing energy in its crystal structure when exposed to radiation. When the TLD is heated, it releases this energy as light, and the amount of light emitted corresponds to the absorbed dose. TLDs are small and can be placed on or inside the patient, making them ideal for patient dose verification. However, they do not provide immediate results. In summary, ionization chambers are best for accurate, real-time calibration, while TLDs are more suitable for patient dose monitoring. In conclusion, dosimetry is a fundamental component of radiation therapy that ensures accurate and safe dose delivery to cancer patients. The gray is the primary unit used to quantify absorbed dose in treatment, planning, and delivery. Ionization chambers provide precise and reliable measurements for machine calibration, while TLD are useful for verifying patient dose. Together, these dosimetric methods helps achieve effective cancer treatment while minimizing unwanted radiation effects on healthy tissues. I think that's all from me and my group members. Thank you for listening.